All right, number 8, you got a box sliding or a carton sliding on a ramp at an angle. They show you what coordinate system would be best, and this is really for every ramp problem, having one axis perpendicular to the ramp and one axis parallel to the ramp. Makes your life a lot easier when you start breaking down the vectors into different components, especially for this problem, because they're asking you how far, if you push the box up the ramp with a speed of 3 meters per second, they're asking you how far up the ramp it will go. So we know at some point you're going to turn this problem into a one-dimensional motion problem along the x direction or along the ramp. So when you're analyzing the forces on it to try to come up with what acceleration it will have, it would be pretty useless if you came up with this set of axes, x parallel to the ground and y perpendicular to the ground. Because if you knew the x acceleration in this set of axes, you couldn't then work the problem along the ramp. It would be really ugly. And generally, on a ramp, you want one axis lined up with the ramp and one axis perpendicular to the ramp. So that's what we'll do. And before you can even answer part A, you've got to do a lot of work. And you've got to analyze all the forces to come up with the acceleration. So to do that, you need a free body diagram. The carton will have a reaction force pushing up, not up, but up and to the right on it from the ramp. Call that R. It will have a weight, which is straight down. Call that mg. And there's no friction, so there's nothing else. There's no rope attached to it. So there's no other forces. These are the only forces acting on it. And remember, our axes are perpendicular to the ramp and parallel to the ramp. So the vector r is already on the y-axis, but the vector mg, or the weight, is not on either axis. There's a component on both. So it helps later in the problem if you go ahead and resolve the weight into two components. This angle will be the same angle as the ramp itself. And there's a lot, not a lot, but you can figure that out again. If you forget that this will be the same angle as the ramp of the incline, look at this over here. So this is theta, this is theta. That's the same angle. This and this. Then you can think that here is 90 minus theta. And then you got another right angle that 90 minus theta is part of. And so the complement to that is 90 minus theta. So this ends up being theta. And this angle is the extension of the reaction force between that and gravity, straight down. This will generally be true for ramps. So if you just remember that if you extend the reaction force line, the angle between that line and weight is the angle of the ramp, you can really speed up and work these problems faster. You don't have to, though. If you need to, you can rederive the angle. Okay, so sum of the forces in the x equals mass times acceleration in the x, and sum of the forces in the y equals mass times acceleration in the y. So just like in projectile motion problems where you have to split the problem up into two different dimensions, when you're dealing with forces acting on an object and there are two different dimensions, you split it up into x and y, and you don't use variables from one and the other. So the only force in the x direction is that x component of gravity, which would be mg sine theta equals max. The only force in the y direction, well, there's two. There's a reaction force and then a component of gravity. So r minus mg cosine theta equals, and in the y direction we know that the carton is staying on the ramp, so there's not going to be any acceleration. So the right side of Newton's second law is 0 over here. So if we need it later, we know that r equals mg cosine theta. I don't think we're going to need it for this problem, though. If there were friction, you would need the reaction force to calculate what the friction was. On the left, in the x column, there's an m on both sides that will cancel out, and so we know that the acceleration along the ramp is g sine theta. All right, with the numbers we have in this problem, the acceleration in the x direction will be 10 times the sine of 30 degrees, which is just a half. So the acceleration will be 5 meters per second squared in the x direction. And remember, our x direction is pointing down the ramp. So it is a positive acceleration because of the way that we defined which way our x-axis was pointing. To work the rest of the problem, it's really just one-dimensional motion along the ramp, and all of the equations that we use for one-dimensional motion will work here, like s equals ut plus 1/2 at squared, or v squared equals u squared plus 2as. Those are valid because the motion is just in one dimension, and we know the acceleration is 5 meters per second squared. So how far up the ramp will it go? We know that the initial velocity is 3 meters per second, but because we define down the ramp as positive, if you push something up the ramp, that's a negative velocity. We know acceleration is 5 meters per second squared. We know at the top of the path, the highest it gets, in that moment, it will momentarily stop and have no velocity. So the final velocity will be 0, and that sets the highest point. And we're looking for displacement in the x. So with these variables that we know and the one we're looking for, it makes me think we should use v squared equals u squared plus 2as. So 0 equals negative 3 squared plus 2 times 5, and then solve for s. So the displacement will end up being negative 3 squared is 9, but to move it to the other side, you subtract, so negative 9 divided by 10 equals negative 0.9 meters. That's displacement, which for our coordinate system is just telling us that it went up the ramp, because down the ramp is positive. Part A of the question is just asking how far up the ramp will it go. So you need to interpret the displacement you found to answer the question they're actually asking, which is just a length up the ramp. So it goes 0.9 meters up the ramp is the answer for part A. Yes, the displacement is negative 0.9 in our coordinate system, but they don't care what our coordinate system is. They just want to know how far along the ramp it went up. And then B asks how much time elapses before it returns to its starting point. So there's a few different ways you could work this one. One quick way might be to use s equals ut plus 1/2 at squared, because if it returns to its starting point, that is a displacement of 0. And we know the initial velocity is 5. No, the initial velocity is negative 3. The acceleration is 5 times t squared. So this just becomes a formula that you don't even really have to use the quadratic equation for, because both terms have a t in it. So you can rewrite this as 5/2 t squared equals 3t by moving 3t to the other side. And then divide both sides by 1 power of t, and then just solve for t, and you get t equals 6/5, or 1.2 seconds. That's a good problem. It's a problem that IB would really like too, because it combines multiple concepts all into one.